Hey everyone, and welcome to The Explainer. I am so incredibly stoked you're here today because we're unpacking something that is honestly completely mind-bending. We're going to trace the actual spatial journey that a single data packet takes through Starlink's cutting-edge network architecture. If you've ever found yourself wondering exactly how an email, a Zoom call, or a quick multiplayer game command manages to travel from your backyard up into the absolute vacuum of space and back down again, all in literally a fraction of a second, well, you are absolutely in the right place. We're going to make the invisible visible today.
All right, so here is our roadmap for the journey to today. We'll kick things off with the satellite internet revolution, explore phased array antenna technology, launch up into low Earth orbit constellations, navigate intersatellite laser links, and finally, bring it all back down to ground stations and POPs. Okay, diving right into Section 1, the satellite internet revolution, and specifically, how we're solving the age-old latency problem. To really appreciate this new tech, we first got to talk about the historical headache of traditional satellite internet, which is basically just massive distances causing insanely frustrating delays. The mathematical contrast here is staggering. Traditional geostationary or geo satellites just hang out way up there at 35,000 kilometers away from Earth. Because your signal has to physically travel that massive distance, you end up with this sluggish latency of over 600 milliseconds. If you've ever tried to have a real-time conversation with a delay like that, you know it's a total nightmare. People constantly talking over each other, right? But Starlink's low Earth orbit, or LEO approach, places their hardware at an altitude of just 550 kilometers. By radically shrinking that distance, they're able to deliver fiber-like latency of roughly 20 milliseconds. To put that into perspective, these satellites orbit 65 times closer to Earth than traditional providers. 65 times! When you realize that, the secret to Starlink's success really just clicks into place. Your data packet barely even has to travel to reach space anymore. This crazy proximity is the foundational secret to unlocking high-speed, low-latency applications for places where laying traditional fiber is just never going to happen. So, the packet's journey officially begins. Let's move to Section 2, Phased Array Antenna Technology. This is the very first stop, sitting right in the user's backyard. Think about the physical hardware for a second. How in the world does a completely flat dish manage to track a satellite that is flying by at an astonishing 17,000 miles per hour? Traditional dishes, they have to physically pan and tilt to point at a fixed spot in the sky. But these LEO satellites, they are constantly racing across the horizon. Well, the secret sauce here is a phased array antenna, which utilizes a really clever concept called beamforming. Instead of acting like one big physical catcher's mitt, imagine the dish as a grid made up of hundreds of tiny individual antennas. By microscopically adjusting the phase, or the exact timing, of the signal coming from each of these small antennas, the dish actually creates a highly directed electronically steerable beam. So the absolute game changer here is that it tracks these incredibly fast-moving targets purely through electronics. The dish itself literally never physically moves once it's set up.
So why does this matter so much for you and your data packet? Well, first off, electronic beam steering allows for seamless satellite switching. As soon as one satellite starts moving out of range, the antenna instantly bends the beam to catch the next one coming over the horizon, completely preventing service drops. Plus, getting rid of moving mechanical parts is a massive boost for durability. If you're relying on this thing in the middle of a brutal winter storm, you really don't want to be worrying about a motor freezing solid or a gear breaking down. It's just a flat, highly durable bridge straight to the sky.
All right, our data packet is successfully beamed up from the phased array on your roof. Section 3, Low Earth Orbit Constellations, takes us directly into orbit at that 550-kilometer mark.
Now, Starlink isn't just a handful of satellites floating around. It is a staggering constellation of over 7,500 satellites creating this vast, interconnected digital mesh that entirely encircles the globe. They use autonomous navigation to hold their exact positions, basically flying in total harmony to blanket the planet in constant coverage. And this whole idea of a digital web encircling the Earth, that is what fundamentally solves the rural broadband problem. See, unlike older legacy systems that will totally drop your connection if your one specific satellite gets blocked or goes offline, this overlapping network maintains multiple simultaneous connections. Your data packet always has a satellite ready and waiting to catch it.
But honestly, here is where the journey gets straight up sci-fi. Section 4, Inter-Satellite Laser Links, or what we can think of as the space routing web. Our packet is up in space, but let's say it needs to travel halfway across the globe.
Instead of bouncing the signal straight back down to Earth right away to travel over standard terrestrial cables, these satellites actually talk directly to each other.
They use optical transceivers, which function a lot like tiny, highly precise space telescopes, to fire your data, encoded into actual laser beams, right through the vacuum of space. And what's truly mind-blowing about the physics here is that light literally travels faster in a vacuum than radio waves do when they're trapped inside traditional glass fiber optic cables down on Earth. So routing your data through space lasers actually speeds up the pace of delivery.
Let's break down exactly how this inter-satellite link, or ISL routing, actually works in real time. First, step 1. The satellite has to constantly track its neighbor's position, which might be hundreds of kilometers away. Then, step 2. It aims that optical transceiver with absolutely pinpoint accuracy. Step 3. Your data gets transmitted as a stream of incredibly rapid light pulses. And finally, step 4, as the satellites orbit and move out of optimal alignment, they execute a seamless handoff to the next satellite in the chain. It is, quite literally, a high-speed orbital ballet.
Now let's talk network topology for a second. I want to slow down just a bit here because the mathematical geometry behind this is actually fascinating. Originally, you might assume they'd use a plus-grid topology, connecting a satellite to its 4 direct neighbors in a simple star pattern. But engineers realized that an X-grid design, using a rectangular topology, minimizes connection overlaps. By simply changing the math and the geometry of how these satellites link their lasers, the X-grid design actually reduces the average number of hops a data packet has to make by a factor of 2. And in networking, fewer hops directly equals less latency and faster internet for you.
Okay, so our data packet has crossed entire oceans at the speed of light in a vacuum. Now it is time for the final descent. Section 5, ground stations and POPs, bringing the signal back down to Earth.
At the end of the day, to load a website, your packet eventually has to connect back to the global internet backbone. And that's where ground stations come in. They act as the critical bridge, grabbing that laser-routed signal down from the satellite and feeding it right into terrestrial infrastructure, seamlessly connecting your space-traveling data to standard Earthbound data centers.
And to make this work smoothly without creating massive bottlenecks, you need serious terrestrial infrastructure. Right now, there are over 140 gateway sites currently online in North America alone, just constantly catching these signals from the orbital mesh. And moving beyond those gateways, there are over 16 major points of presence, or POPs, scattered across North America. These POPs are essentially the heavy-duty data centers. Now, why build so many? It all comes down to redundancy. If one POP experiences a terrestrial fiber cut or a sudden power outage, which, let's be real, happens all the time globally, Starlink's system immediately fails over. It instantaneously reroutes your packet to another site, entirely preventing any noticeable service outage for the user.
Wow, okay, we've covered a ton of ground today, and space. Let's bring all these micro-elements together into the macro view for a final section, the journey summarized.
The real magic here is how flawlessly these distinct, incredibly complex technologies hand off to one another in the literal blink of an eye. Your request starts at step 1, your flat phased array user terminal, which electronically steers a beam to step 2, a low Earth orbit satellite zipping by 550 kilometers up. By step 3, your packet is being shot out of an optical transceiver, riding a literal laser beam through the vacuum of space across the constellation web. Step 4, it beams back down to a terrestrial gateway, and finally, step 5, it hits a secure, redundant POP data center to merge with the global internet backbone. And again, it does this entire sequence in mere milliseconds.
Which leaves us with a massive, kind of provocative question for the future. When we look at the upcoming V3 satellites, which are going to be launched by Starship and will add an unbelievable 60 terabits per second of capacity to the network per launch, combined with these space laser links that just entirely bypass so much ground infrastructure, are we witnessing the beginning of the end for traditional terrestrial internet dominance? It is a truly fascinating paradigm shift in global connectivity. I really hope this explainer helped demystify the incredible journey happening right above our heads every single day. Thanks so much for learning with me, and definitely keep questioning how the world connects.